I'd like you to welcome to the second talk of our colloquium. Today we have Andrew Lamsden, and he will give a talk about scalable second-order methods for machine learning and AI. But before we listen to his talk, we have a second speaker today. Let me introduce you Dr. Samuel J. Bentley. He serves as LSU Vice President and is the Billy and Ann Harrison Chair in Sedimentary Geology. He got his PhD in Coastal Geology, Oceanography from Sunny Stone Brook in 1989. And his current research involves field laboratory and modeling studies of sediments and stratigraphy on continental margins of ocean basins, including the Mississippi Delta. We are very grateful that he didn't want to miss the opportunity today to say a couple of words as an opening statement to our second seminar in the series of the Cairo Colloquium for Artificial Intelligence, Research and Optimization. So welcome, Sam.
Thank you very much, Patrick. It's a great honor to offer introductory comments today, preceding Dr. Lumsdaine's talk, and also in the second talk of the Cairo Colloquium series. I'd like to thank Hartmut and the program committee, including Patrick and Katie Bailey and all the others who've been involved in bringing this up to speed. And this is a very exciting time for us. And so I just want to put this in sort of the context that I see the work that you all are doing. So I think we can all recognize that AI and machine learning and the various other related tools that you know so much more about than I do really pervade many aspects of our life today, whether we know about them or not. And the same is true for research on the LSU campus. I mean, I don't think I've been in one proposal defense or read one dissertation in the last couple of years, even in coastal geosciences, that doesn't include some aspect of artificial intelligence or machine learning or deep learning or some approach like this that to sort of enhance the research. So it's been a very exciting time, and so there are many research labs not only in coastal geology but across LSU who are using these approaches, and it's really cool. There have been some great successes and some great opportunities that we're trying to go after. I mean, the Cairo proposal that Hartmut led back in the fall. I mean, we all know how much work goes into developing a major proposal. And we also know that even if a proposal that scale is not successful the first time, the work that goes into it is not lost. And so it's a great effort to bring the team together at LSU. We've also had success in other sectors of campus. Our deep drug team, led by Supratik Mukhopadhyay and Michael Berlinski, has done great work on drug discovery, first for drug-resistant bacteria, and most recently working on developing drugs for the treatment of the COVID virus. Even in academic programs, this is becoming much more front and center. I'll just give you a quick story on that. About 2 weeks ago, I received a note from the provost, my boss, with a short statement from the University of Florida outlining their All right, how about that?
Okay, you are back. Perfect.
Yes, gone from our power just went out, so I'm on my cell phone. Shall I wrap up rather quickly?
Yes, so we can start the talk because we're a little bit late.
Yeah, that's fine. Well, so all I wanted to wrap up with is that University of Florida and LSU and many other universities are really looking for ways to capitalize on the power of machine learning and AI. And I'm really excited that we've got this opportunity not only to tackle the using it more broadly across our campus, but actually make it a more powerful tool. So I'd like to thank Dr. Lumsdaine for his for joining us today under however crazy and chaotic circumstances. And thanks CCT and the whole production team for putting this together. So thank you very much.
Thank you very much for your welcome remarks. And before we start with Andrew's talk, I would like to introduce him to you. So Andrew Lamsden is an internationally recognized expert in the area of high performance computing, who has made important contributions in many of the constitutive areas of HPC, including systems, programming languages, software libraries, and performance modeling. He works in HPC, has been motivated by data-driven problems, for example, large-scale graphs analytics, as well as more traditionally computational science problems. He has been active participant in multiple standardization efforts, including the MPI Forum, C+ Technical Forum, the ISO C++ Standardization Committee, the One API Technology Advisory Board, and the SciSL Advisory Panel. Open source software projects resulting from his work include the Matrix Template Library, the Boost Graph Library, and OpenMPI. So thanks, Andrew, for giving the talk, and the stage is yours.
Okay, well, thank you, Patrick, for the introduction, and thank you, CCT, for the invitation and opportunity to present. I'll start with just maybe a quick story from my own life. So neural networks and machine learning and AI is nothing new, right? I mean, in AI, everyone's heard of the Turing Test, and that goes back to really the very first days of things we think of as being computer science with Alan Turing. And so even from the very beginning of computing, people were thinking about how to use these things to replace, very high level capabilities of humans, really replacing, creating, if you like, thinking machines. And so and there have been, periodic waves of interest that kind of ebbed and flowed over the years. One of the peaks was when in the past was just when I was starting my own graduate program. And at the time, my advisor made the kind of offhand comment that neural networks seem to always be the second best solution to every problem. And that's changed recently. And of course, I mean, some of the things we see machine learning doing is just astonishing, actually. We're really starting to approach the levels of a sufficiently advanced technology. And so if we think about what enabled that, though, that was really the emergence of, I mean, I'll just point and just say that it was really just the emergence of GPUs as a particular type of compute resource that was so well matched to the needs of neural networks or deep neural networks that we were able to suddenly take advantage of what was really possible with these types of systems. But there's still limitations despite that. And what I want to try to talk about today is really how we can maybe make another similar kind of leap. So with the emergence of TPUs, we have this phase change, if you like, or quantum leap from neural networks being the second best solution to all problems to really being the best solution by far. I mean, if you look in the, particularly in the computer vision community, machine learning has completely dominated all approaches for solving typical computer vision problems. And so my hypothesis right now is that by now scaling machines and systems out, by taking advantage of large-scale parallelism and supercomputers, we can achieve another sort of quantum leap in the capabilities of these systems. And the limitation right now in what we can do with deep learning and deep neural networks is really based on how long it takes to train these systems. And the training time then constrains the turnaround time for doing experiments and doing research and creating new types of systems. And so the problem we run into, and we'll look at this in more detail during the talk, is that because of the inherent nature of some of the current approaches for doing training, we can't just throw more hardware. We can't just parallelize them in the way we'd like to be able to speed things up and to scale out. And what we're proposing and what this talk is about is how we can use higher order methods, and particularly second order methods that can, first of all, give us better convergence so that we can get to a solution in a fewer number of steps, but also enable more ready parallelization so that we can make those fewer steps also in a shorter amount of time. And that's true even though in terms of total amount of computation, the cost per step or per iteration might be higher with these second order methods. So the ultimate goal, I guess, of what we're trying to do with Cairo, the project, is to reduce the training time in deep learning from weeks to hours or even minutes, and really achieve this next kind of phase change and quantum leap in capabilities of machine learning, similar to what happened when GPUs arrived on the scene. And so what I want to kind of cover in the talk is, first of all, motivate the second order methods by looking at machine learning training as an optimization problem. Just quickly talk about some of the first order methods, particularly stochastic gradient descent, and then spend the bulk of the talk covering different classes of second order methods, and then finally present some experimental results that we have with the Mns data set. So neural network training. This is just a quick overview again, and introduce some of the notation we'll be seeing. So one way of thinking about what the neural net does is it's just basically a nonlinear function of some input x, x sup 0, and some output it'll produce x sup L. So x0 is the input, xL is the output. The nonlinear function is n, and it depends on these parameters theta. And the whole game in training is trying to find the best possible settings for those parameters so that we get the neural network to do what we want it to do. And typically we characterize that task in terms of a loss function. So for instance, in a supervised learning situation, we might just compare the output of the network against some ground truth, and then create an objective function for overall training, which might be the sum of the losses over all of the inputs, where we compare, again, the output of the neural net function, or the loss of the output of the neural net function with the ground truth that we have for that known input. And so our training goal is to find this very best set of parameters to make that objective function as small as possible. And so the approach that's typically used is we have we're going to iterate and compute successive values of these parameters theta. So theta of k plus 1 will be the previous value of theta plus some update. And the two pieces involved in making that update are, first of all, finding the direction p that will maximize or decrease in our objective function. So our goal is to make as we take steps, we want to make the objective function smaller and smaller. So we want to take a step in a direction that will maximize the decrease in J. And that turns out to be in the direction of the derivative, or in the opposite direction of the derivative, which is the transpose of the gradient. So sometimes the derivative and cost function, derivative of the cost function and gradient of the cost function are used somewhat interchangeably. They're essentially the same, except one is the transpose of the other. I'll typically talk about the derivative rather than gradient, but often in the machine learning literature, people talk about the gradient. So the steepest descent approach then that we can use is just based on picking our step sizes in the direction of the gradient, p, or the transpose of the derivative, and updating our parameters accordingly. So in this formulation, we're computing this gradient using the entire training set. That doesn't always work in terms of the rate of convergence and so forth, and we'll talk about that in a little more detail. So another approach, and this is where we really get to the stochastic gradient descent, is that rather than forming a gradient based on the entire training set, we'll just take one element at a time from the training set, compute the gradient based on that, and then take a step, update the parameters based on that one element. And we can go in between all the elements or just one element and use mini batches. But the idea is that we, in stochastic gradient descent, as we in some sense do, update incrementally for each member of the training set. So the entire stochastic gradient descent with backpropagation algorithm looks like this. And what I want to try to get across here maybe is not so much that everyone memorize this for the test that's coming up at the end of the talk, but rather try to motivate where some of the parallelization might be. So there are two kind of primary steps in computing the gradient. So this is typically done with a technique known as backpropagation. So first we feed the signal forward through the network. So for each stage in the network, we compute the X values in successive stages from X0 to XL. And then we go backwards, computing gradients and updating the parameters as we go. This turns out to be a very sequential process. So you can see we have 3 nested loops and they seem to all depend on each other. If we look a little more carefully at the loops, I mean, so the outer loop is the iteration count that we're doing. We can't really, do those simultaneously. And similarly, on the inner loop, we're feeding the signal forward through the network and then feeding it backwards. We can't really do any of that in parallel. That's inherently sequential. With the batches, though, as I said, there's in between doing one sample at a time and doing all the samples at a time to compute gradient. We can do some finite number of them, some subset of them, and this is sometimes called using mini batches. And in that case, we can get some parallelism because we can do each of the members of the mini batch in parallel. But unfortunately, it turns out, and this is just borne out empirically, as we increase the size of the mini batches, so as we increase the size of the mini batches, we increase the amount of potential parallelism. But as we increase the size of the mini batches, it also, at least for stochastic gradient descent, this won't be true for the second order methods, but for stochastic gradient descent, increasing the mini batch size actually slows the convergence of the algorithm. So there's limitations there. We also have some potential parallelism, and we'll look at this in the next slide in a little more detail, at the lower level in terms of doing these low level computations. But in some sense, that's been well optimized by the GPUs. I mean, this is in the feed forward and the back propagation steps. getting the maximal performance there has been where the GPUs have really made the contributions. And so again, what we're trying to do is add another dimension of parallelizability and scalability. And really the place we'll be attacking this primarily is in parallelizing across the batches. And we can think of this or look at this graphically. So if we have a problem, and this is just shown very stylistically, I drew this myself. I hope it makes sense to other people. But given some training set input with a batch size B, what, again, the kind of parallelism we're proposing is that we can split the batch into different pieces and do those in parallel with copies of the model on different machines. The other types of parallelism I mentioned, so for instance, with the model parallelism, we can do different parts of the model on different nodes or on different processors. But again, for the model parallelism and pipelining parallelism, that's really optimizations done on a single node and has been very well accomplished by using GPUs. So second order methods, what are they? The idea is that rather than just trying to maximize how much smaller we can make the cost function, let's go ahead and actually find the minimizer of it. So the gradient descent approach, we're trying to compute an update so that at each step we're going to make the cost function smaller. With the second order methods, we actually want to find the minimum of the cost function. And so from calculus, as we know that we find the minimum or maximum of different functions where the derivative is equal to 0. So our task now, or one way of phrasing second order methods, is we want to develop methods where we have a solution that will drive the derivative or the gradient of the objective function to 0. And so the derivative is a nonlinear function of n variables and n unknowns. The kind of classic approach to solving problems like that is Newton's method. So I'll be writing f as we go through some of the rest of the slides rather than dj, but realize that f is what the function we're trying to minimize or trying to drive to 0, and that's actually equal to the derivative of the cost function. And what Newton's method does is it uses linear approximation based on a Taylor expansion around the current set point to compute an update of the state. So we basically invert this derivative of the derivative of the cost function and use that to compute our increment. So this step on line 4, where we compute d equal to the inverse of the derivative of the cost function, and we'll refer to that as the Hessian. When we invert that or solve the linear system really for d sup k, that's our update step now with the second order methods. And one appeal of this method is there's no actual limit on the batch size, and we can apply this with a full batch and have maximum parallelism in that case. Unfortunately, so we think about things in terms of dimensions of things. So I mentioned that the nonlinear function f, the derivative of the cost function, is a function of n variables, and it produces n variables as a result. It maps Rn to Rn. Then the Hessian is going to be a matrix that is n by n. So if, just a modest sized network these days might have a few million parameters. That means we would have a matrix that's 1,000,000 by 1,000,000 or a few million by a few million. And that, 10 to the 12th entries is more space than is, we can reasonably store even on a supercomputer, and is more running through it, iterating through it is more work than we'd want to do. So we might not actually want to form that. And so we'll be looking at ways of approximating the Hessian. In fact, another reason to think about approximating the Hessian is if you actually write it out, it's very complicated. It's a very large scale entity and is very expensive to compute and store. So the thing to remember, even though in the rest of the talk, we'll be looking at second order methods. Second order methods are based on using the Hessian. All of these approaches are going to use the Hessian without using the Hessian. So kind of remember this picture from this classic movie. There is no Hessian, even though we'll be talking about using the Hessian. And we'll see what we mean by that in a minute. So the real formulation of the Newton iteration that we're going to use is the inexact Newton method. And the idea there is, rather than in the step of computing our update where we solve a linear system, we are going to just produce an approximation to the linear system solution. And that could be by using an approximate solver, or using an approximate solver with an approximate matrix, or using an exact solver with an approximate matrix, or so on. But the idea is that we produce a solution that's just approximately the correct solution. And that's fine, right? I mean, we're in an iteration anyway of trying to approach the best value of theta. So if our update isn't exactly the best, we're going to keep iterating anyway. And under some suitable conditions, for how the accuracy or how these approximations go, we can still get the desired kinds of convergence that we would want from second order methods. So the first inexact Newton method we're going to look at is based on using a Krylov solver for solving the linear system solution. So these are the class of methods. For instance, that conjugate gradient is the canonical exemplar. And this is a related algorithm to conjugate gradient, conjugate residual. And again, even though the whole algorithm's here, this won't be on the quiz. The point is that within these algorithms, there's an important step, and that is computing the matrix by vector product. So if you look in a textbook on conjugate gradient or conjugate residual, within there's a step of computing A times X. Well, in our case, that A, the matrix that we're trying to invert, is the Hessian, or it's the derivative of this nonlinear function f. Well, we can take advantage of that to compute the approximate result of applying that matrix to a vector. And we can do that by, again, relying on Taylor series and computing the value of the function f at theta naught plus some small perturbation in the direction of the vector we're interested in multiplying by, and then subtracting off the original f of theta naught. And that's in step 10. And so the idea is that we can approximate our application of a matrix, or approximating this key operation inside of the Krylov solver of a matrix times vector product by just using our nonlinear function application. So that's, in this case, that's how there is no Hessian, right? We're just using the nonlinear function, which, as a reminder, is the gradient or the derivative of the cost function, which is something the different frameworks like PyTorch or LibTorch are optimized to compute for you. So this, as we'll see when we, at the very end, when we talk a little bit about implementation, this fits nicely into the way these frameworks are already built. Now, the second class of second order methods are, instead of inexact Newton, these are sometimes called quasi-Newton or secant methods. And the idea here, we can kind of motivate from the one-dimensional case. The idea with Newton's method is we're approximating our function that we're trying to solve by linearizing it at a certain point and assuming that that linearization will take us to the exact solution. It doesn't, but then, you know, we keep applying that linearization process until we converge to the exact solution. Well, if that derivative isn't available for some reason, we can approximate the derivative, right, by taking a chord across the nonlinear function. So we can evaluate the nonlinear function at 2 points, take the difference between those 2 points, take the difference between the function evaluated at those 2 points, divide them. That gives us the slope, which is an approximation to the tangent line, right? And that gives us, we can then use that as an approximate value for the Newton solver. Now, the problem is we can't quite, in the case of vector multidimensional quantities here, we can't quite do that division to get the slope of the line. What we do instead is we set up what we call the secant conditions. So in the direct case, we are looking for a matrix B sub K, that satisfies the secant condition. So that B times the delta X is equal to the deltas in F. And we can flip that around as well. So there's a dual condition. So we can think about, rather than trying to find this B, we could find the inverse of B, or we'll call that H here, so that it satisfies this condition that delta X is equal to H times the deltas in F. And so we can basically write out our Newton methods or quasi-Newton methods with these secant matrices. So in the case of the direct method, we have a step where we solve a linear system based on B. What's interesting in the case of the dual or the inverse methods, since the matrix that we're approximating is in fact the inverse of B, we don't have to solve a linear system. We just need to do a matrix times vector product with the matrix we're approximating. And then the big step, or the thing that we talk about in the next slides, is what is this update for B? How do we make that approximation to B or to equivalently to H? And usually that's done by using the secant condition and then adding some regularization to determine what B needs to be. So in Broyden's method, for instance, we apply regularization that we are going to compute B that is a minimum norm, minimus Frobenius norm. And again, that has a linear system solve. We can apply different types of regularization, and these will give us different updates at this step. And this gives us other methods like Davidon-Fletcher-Powell and SR1 and Broyden symmetrized Powell, or Powell symmetrized Broyden, and so forth. Similarly, for the dual methods, we have an update step, and again, different regularization gives us different methods. But the important thing to note again is that there's not a linear system solve. So this becomes a very cheap method in some sense, because we're just doing this matrix by vector product. Now, I kept saying there's no matrix, and here again we have a place where there's a matrix. So in the previous one we had to solve a linear system based on a matrix. Here we're saying we're doing a matrix by vector product. Again, we're going to do this without actually forming the matrix, because again we really just need to form the matrix times vector product in either case. Right, so in the case where we have the inverse of the matrix, we just need to form the matrix vector product within the nonlinear algorithm. In the case where we need to do the linear solve, we can again use a Krylov solver and do the matrix vector product accordingly in the following way. So if we look at the update for Broyden's direct method, for instance, it's equal to the previous value of B plus an outer product term. Well, we can recurse back on what all of those terms are and just get a summation for what the matrix is. It's the initial value B0 plus the summation of outer product terms. Well, if we want to multiply that matrix B times some vector, we can do that by applying this outer product term, which now will just turn into a bunch of inner product terms times the previously stored vectors. So this just becomes almost like a Gram-Schmidt orthogonalization step, but it is the amount of work isn't the size of the Hessian that isn't there, but rather is the based on the number of vectors we've stored for the outer product terms. Now there is the one term here, this initial term of B0 times P that we need to compute. And again, we just need to compute the result of this. We don't need some initial actual Hessian. So it's typical to, for instance, just use the identity as the initial value for B, or some scale diagonal, or something that's very, very quick to compute with. And so again, we have Hessian-based method without a Hessian. Now, what's really interesting is that, and this is something that's kind of work in progress and something we just kind of stumbled on, is that you can think about even higher order methods than Newton's method, so third or fourth order. And you can create, the idea is that rather than trying to just compute the slope, a straight line, to approximate the nonlinear function, we can try to fit a second order polynomial, we can try to fit a quadratic or a cubic. And if we do that, of course, the terms we're trying to compute might seem like third order. Well, that's suddenly the derivative of the Hessian, which the dimensionality blows up even more, and then the derivative of the derivative of the derivative of the derivative of the Hessian, that blows up even more. Well, it turns out we can compute, kind of following the theme we've been seeing, we can compute the effect of the third order term by just adding a small correction term to the update to D. So this starts to have the actual kind of the feel of linear multi-step methods from the ODE solution literature. And again, this is work in progress, but it's just really interesting and seems to, and we're hoping will solve some of the problems we or the community seems to run into sometimes with these second order methods. So implementation, I alluded to before that we can take advantage of some of the structure of the problem and how when we're talking about computing the nonlinear function or the gradient, we're really talking about doing this forward and backward step that we saw at the beginning with stochastic gradient descent. For the first implementation I did actually was just in my own, just in C++. So this was just the Newton method. This is sort of line from line from the Newton method slide we had before. There's a Krylov solver step in the middle that we can parallelize kind of at the node level, and get the mini batch parallelism, because again, in the step of doing the matrix by vector product, we are just doing our forward and backward sweeps to compute the gradient. And this is something, I don't know if Hartmut's on the line, but it would be something he would appreciate, doing this in the implementations in heavily parameterized C++. And so this is just written out pretty much like you would see the conjugate gradient algorithm in a textbook, including a matrix by vector product. But again, we can overload that to actually mean what we want it to mean, which in this case is this nonlinear function evaluation, rather than an actual matrix times vector product. And we can apply the same, or did apply the same idea within the context of PyTorch. So there, the basic training step looks like this. This is actually the C++ interface to PyTorch. So the training is just basically an outer loop going over batches of the data, and then taking a step with the optimizer, where we pass in this thing called a closure, which basically just the optimizer uses to do its gradient computation. And so what we have in, or how this maps to our original, how the PyTorch maps to the original algorithm is, again, the place where we're doing what looks like this function evaluation here, f of x, is actually this gradient computation. And then these different steps where we're doing vector operations, x equals x plus alpha p, and so forth, are just tensor arithmetic that comes also with PyTorch. And so the implementation in PyTorch looks much like, again, the pseudocode for the algorithm, and also looks a lot like the other C++ implementation we had before. So I'll skip very quickly. We get to our results. So the final thing I just want to show is how these have worked on kind of one of the canonical machine learning problems, the Mns Data Set. For those of you who haven't done MNIST problems yet, is the Mns Data Set is 60,000 handwritten digits. Well, it's really two data sets. There's a training data set and a testing data set. So the training data set has 60,000 handwritten digits, and then the testing data set has 10,000 handwritten digits. And the goal is to train a network so that it can achieve the highest accuracy in terms of recognizing the digits in the testing set after having been trained by the digits in the training set. And so we applied I'll show experiments for both the Krylov-Newton method as well as the quasi-Newton methods, the secant methods. But in applying the Newton-Krylov method, in our first experiment, I was just measuring here the norm of the derivative of the cost function, the norm of the gradient, as a function of iteration. And you can kind of see the Newton and the Krylov performance here. So the plateaus that you see are basically every Newton step, after which we have some Krylov iterations, and those drive apparently the solution low. But when we kick back out to the nonlinear solver, it's not, we didn't actually make that much progress, so we pop back up to another plateau. But basically over time, the iteration or the gradient goes to zero, which seems like it would be good. Except if we actually look at the norm of the cost function itself, or equivalently, we could look at the accuracy, we find that after one step, we've gotten stuck and don't make any more progress. And so what's happened here is we've gotten stuck in a local minimum. So in the formulation of the second order problem, we just are looking for a place where the derivative goes to 0. It doesn't necessarily guarantee that that's the optimal or even a great place. So in this case, we've gotten stuck at a not very good place. So one important open question really for second order methods is how to achieve good global convergence behavior. What I did in this case to try to fix that problem was used a few steps of stochastic gradient descent to initialize the second order method. So this graph shows 3 experiments of on MNIST. The blue line is just using stochastic gradient descent, and this is showing the accuracy of at each epoch of the neural network at that time, the accuracy with the test set. So the stochastic gradient descent in blue, and you can kind of see that it kind of converges, but just kind of jumps around. In orange is the Newton-Krylov method, and there I initialize it with after 1 step of the stochastic gradient descent, and so it converges okay. Still kind of trying to catch up to stochastic gradient descent. With the green line, I took 5 steps of stochastic gradient descent and used that to initialize the second order method. And so there you can see that it starts off well and continues to stay above the stochastic gradient descent. And so this is okay, right? But what's remarkable is when we look at this not as a function of epoch, but convergence as a function of time. So here are the same data points, but again plotted with as a function of elapsed time rather than epoch. And so here we can see that the second order methods are much quicker in terms of elapsed time to converge than the first order method. And then finally, I can skip to the last slide for time. We ran those same experiments, adding some of the secant method approaches. So the purple line is using a secant method that's similar to the Broyden method we looked at called SR1. And there it converged, seems to actually, all of the methods here seems to have the best convergence as well as the most rapid convergence. So this is just scratching the surface of, I think, what can be done with these kind of methods. I mean, the stochastic gradient descent approaches have benefited from years and years and years of polishing and tuning of the parameters and the methods and so forth. And the second order methods are just starting to gain attention, starting to get the same kind of tuning. But I think there's a lot of work that needs to be done, both in terms of now really implementing some of these methods in problems that are much larger than MNIST. So MNIST is fine. It's kind of always a sanity check on any new approach, but we're in the process now of trying to scale up to doing problems using CIFAR and using larger networks like ResNet. And so and then we also want to do that in the context of instead of this custom C++ or even the C++ stuff in libtorch, do it in the mainstream PyTorch and TensorFlow, so that we can really do apples to apples kinds of comparisons with state-of-the-art gradient approaches. And one of the main goals, and this was one of the main goals of our proposal that Dr. Bentley alluded to earlier, we want to really scale this up. And this was really the other side of these methods, not just that these have good convergence and have some better efficiency on one node, but that they also offer better scalability at a large scale. And so we want to also start looking at scaling and are in the process of really trying to look at how to scale these up using some of the technologies at CCT, most notably HPX and Phalanx. And so with that, I think I'll thank CCT and Patrick and everyone again, and be happy to answer any questions.
Thanks, Andrew, for your excellent talk. Intra is asking, how do recent first-order methods such as ADAM perform in terms of convergence compared to second-order or higher-order methods?
Oh, well, so this is a good question, and this is why some of the experimenting we want to do to really find out. There was a paper that just came out. I haven't had a chance to really read it or try to reproduce the results that did some of those comparisons. Adam and a lot of these other approaches, as I mentioned, are really trying are these super sophisticated refinements on the first order methods. So I think ultimately that they might improve convergence and so forth, but they still have the same limitations in terms of parallelizability. So I think I think the second order methods will, particularly once they have the same level of polishing and tuning and specialist and optimization by the community that first order methods have had, I think they'll be more than competitive with these. But more importantly, they'll still offer the better potential for scalability.
Okay, there's one more question in the chat. I will read it out. Is anybody using minimization methods similar to the parallel tempering used for spin classes?
Okay, I'm not familiar with that. So these are sort of like with these.
Joanna, do you want to speak up and explain a little bit more? We have one more question. I will read it out again. If I understand correctly from the benchmark, the benefits of second order methods are twofold. First, faster computations per iterations. Second, faster convergence per iteration.
Yeah, and with the caveat that you can get faster convergence per iteration into a bad place. We saw that in the very first slides of the experimental results. So there's I think there's also work that needs to be done, as I mentioned, in terms of getting better global convergence behavior for these algorithms, so you don't get trapped in local minima.
Okay. He's asking, may I see some complexity analysis on the computation cost?
Well, I don't have a slide with that now. I prefer to do this one offline because I have to actually think to give the answer. Yeah, I don't have a slide with that, but the main cost in any of these, so I alluded a couple of times to the fact that there's this step, and this was in that closure I showed in the PyTorch example and so forth, but there's a step where we're doing basically the nonlinear function evaluation or the gradient computation or whatever. That's sort of the main cost, is going forward and backward in the model. And so a lot of the complexity, kind of just back of the envelope complexity, people tend to think about, or I've been thinking about in these methods is, how many of those function evaluations do you have to do? And in that case, there's in the stochastic gradient descent, there's essentially one of those for the whole batch, right, per epoch. In these second order methods, there's one of those per iteration, either the Newton iteration or the each Krylov iteration. So so that would be kind of the comparison of epochs, how many epochs in stochastic gradient descent versus how many total iterations of the nonlinear and linear iterations are you doing, and at least in the Newton Krylov iterations. It's not, well, I guess that's true even in the secant iterations. It's basically one function evaluation, one back and forth at each iteration. So but that again is not quite apples and apples, because the again, in stochastic gradient descent, you have to do one sample or one mini batch after another, whereas in the second order methods, we can do the entire batch at once in the forward and backward, and scale that out or do that in parallel. So, yes, that's the best I can do with them off the top of my head for complexity.
Okay, we have one last question. According to your numerical experiments, among these quasi-Newton methods, which one experimentally works better?
That's hard to say, because I don't think there's been enough experimenting done with that yet. And the one that people use the most often is the LBFGS method. So it's the limited memory Broyden-Fletcher Goldfarb-Shannon algorithm. But I'm not convinced that that's necessarily the best. So I think the jury's still out on that question.
Okay. Thanks again for your excellent talk, and thanks again to Dr. Bentley for his welcome remarks. Hope to see you again. Thank you.
Okay, thank you.
Yeah, thank you, Andrew. It was a really nice talk and a really nice overview of the second order methods.
Thanks. It's hard to fit it all into just 1 hour, but no, it's good.
Yeah.